All right, so limiting and excess reactants. The limiting reactant is the reactant that limits the amount of product that can be produced. It's the reactant that we run out of in the course of the reaction. You can also say the limiting reactant stops the reaction, because once we're out of it, the reaction's done. Like in your lab, when we were reacting the sodium carbonate with the hydrochloric acid, the sodium carbonate was our limiting reactant because we kept adding more and more HCl until all of the sodium carbonate was gone. It got used up. Okay? Once we used up all of the sodium carbonate, when you added more HCl, you shouldn't have seen any more bubbles because the reaction was done at that point. Okay? The excess reactant is the reactant that is left over after the reaction is complete. So in our lab, HCl was our excess reactant because we had way more than enough of it. Okay? The process for determining the limiting and excess reactant is this. When you have, you'll be given the masses of both the limiting, or you'll be given the masses of both reactants, and you won't know which one's limiting and which one's excess. You have to do math to figure it out. You're first going to convert them both to moles. Okay, so that's just a mass to mole step, which we've been doing for like a month now. Then, once you have the moles of each reactant, you're going to divide the moles of the reactant by the coefficient from the balanced chemical equation. So in order to do this, you need a balanced chemical equation. Whichever one gives the smaller answer, that is the limiting reactant because it's the least amount in ratio with each other. And then once you've determined your limiting reactant, to figure out the mass of the product that you can make, you want to use the moles of the limiting reactant to do your stoichiometry. Okay? Are we good here? Okay. So now let's do some practice problems. So we have this reaction. We're reacting sodium hydroxide, NaOH, with phosphoric acid, H3PO4. And we're given the masses of both. And we want to know how much sodium phosphate, which is Na3PO4, can we make. What do we need to do to this reaction? Balance it. That should always be your first step. If you don't already have a reaction, write it. This one, it was nice, and I gave you the reaction. Okay? So take a moment to balance this equation. Okay, so when this reaction is balanced, what are our coefficients? What did we get? 3, 1, 3, 1. Wonderful. Okay, so now we're going to go through, in order to figure out the amount of sodium phosphate we can make, we have to first decide which one's our limiting reactant. Because we use the moles of the limiting reactant to calculate the mass of product. So we're going to go through these steps. So we're going to convert each mass to moles. So the 17.82 grams of sodium hydroxide, we're going to have to convert that to moles, and the same thing with the 15.40 grams of H3PO4, we need to convert that to moles. So both of them are just a mass to mole step. So 1 mole of that substance is on the top, and then the molar mass goes on the bottom. So we need to start calculating the molar masses of both of these substances. So now I have the problem set up. So I'm going to calculate the molar mass of sodium hydroxide, which is, anyone there yet? What is it? 40. And remember, we always do 2 decimal places, so we would put 40.00. And then what is the molar mass of phosphoric acid, H3PO4? Anyone there yet? I know. Asking you to do work during class. What is this? 98.00. Just happened that both of these were whole numbers. Okay, so now I have the molar masses of both. I'm going to do the actual math. I'm going to take the grams and divide it by the molar mass to get the moles. So what do we get as the moles of sodium hydroxide? Yep, 0.4455. And phosphoric acid? One five seven one? 0.1571. All right, now, based on, like, the most common mistake people make here is they forget to divide by the moles from the coefficient, or the coefficient. If you're just looking at the moles, you would think that phosphoric acid is the limiting reactant, but we have to compare them in ratio to each other. We have to look at the ratio for the whole chemical equation. Sodium hydroxide has a coefficient of 3, so we're going to take its moles and divide it by 3. Phosphoric acid has a coefficient of 1, so we're going to take its moles and divide by 1. So we would get 0.1571. And what is 0.4455 divided by 3? 1485? Which 0.1485 is smaller than 0.1571, which makes sodium hydroxide my limiting reactant. So now that I know which one's my limiting reactant, I can do the math. Now, on a test or quiz, for example, the quiz you're taking next week on this, say, like, it's going to be a multi-part problem with this. You're going to get points for identifying the limiting reactant correctly. You're going to get points for determining the amount of product that can be made. Say you identify the limiting reactant wrong. Like you said it was phosphoric acid. Bless you, by the way. Say you said that the limiting reactant was phosphoric acid. You'll lose the points for this part. But if you use the moles of what you said was the limiting reactant to find the mass of product and you do that part right, I'll give you the credit for the next part. So I will carry your mistakes through, and because I care about the process, okay? I don't want one mistake early on to, like, it's not going to be like one mistake early on is going to lose you all the points. You'll get partial credit, okay? Or, for example, say you balanced wrong, and that made you identify the wrong limiting reactant. Part A will be balance this equation. Part B will be identify the limiting reactant. If you do part A wrong, but then part B is right for your wrong part A, I give you credit for part B. Does that make sense? Okay, so it's possible to technically get the wrong answer for everything, but it's right for your original wrong balancing. Okay, and you'll get like the majority of points there. Okay, so now that we've identified our limiting reactant, we're going to use the moles of our limiting reactant. As said here in number 4, we're going to use the moles of the limiting reactant to do stoichiometry to find the mass of product. So how many moles of my limiting reactant do I have? Yep, 0.4455 is the moles of my limiting reactant. That was supposed to change to green. Green, there we go. 0.4455 moles of sodium hydroxide. We're going to start here and convert that to grams of our product. So we're going to have to go from moles of sodium hydroxide to moles of Na3PO4, and then from moles of Na3PO4 to grams of Na3PO4. So it's mole to mole to mass. You could go back to the original grams of our limiting reactant, but your first step is going to be what we already did, so save some time and save some space. So we're going from moles of NaOH to moles of Na3PO4. What numbers go here? 1 on top, 3 on the bottom. Where did you get those numbers from? Coefficients in the balanced chemical equation. Okay. And then our last step will be from moles of Na3PO4 to grams of Na3PO4. What number goes with moles? 1. And what do we put with grams? Yep, the molar mass on the periodic table, mm on the PT. So somebody calculate the molar mass of Na3PO4 for me. The H3PO4 was 98. We haven't calculated this molar mass yet. Yawning is banned in this class because it makes me yawn. All right, what do we get? Yep, 163.94 is the molar mass of Na3PO4. And now we can do the math for this problem. And this will tell us how many grams of Na3PO4 we could actually make. And again, it's based off of the limiting reactant because the limiting reactant is the substance that we're going to run out of. Okay? So it's going to limit how much product can be made. What do you get? Yep. 24.35 grams of Na3PO4. Okay? So that's the first part. Honestly, if this were like a quiz question, this would be part A would be the reaction, part B would be determining the limiting reactant, part C would be figuring out the mass of product that could be made. Part D would be on the next page. Are we ready to go? Okay. Part D, oh, sorry, next page for you guys after this. Part D would be determining how much of that excess reactant remains after the reaction is done. When we did our POGL last class, that was last class, right? And I know some of you guys were taking your SOL and then some of you left early. But when we were doing the POGL, we did this part in the POGL as well. Okay, so none of what we've actually talked about today is anything new for the class in general, but we're just doing more practice problems. So to figure out how much of the excess reactant remains, because remember, some of it's going to be left over, you first have to figure out how much you used. How much you used. And the easiest way to do that is to take the moles of your limiting reactant, so what you started with to find the mass of product, take the moles of the limiting reactant and convert that to grams of your excess reactant, and that will tell you how much of your excess reactant you used. Then you're going to subtract that from the mass of excess that you started with. Okay? Have you finished writing down the 8 letters from this page that you have to write down? Okay. So, we're going to apply it to that problem. This would be, like I said, this would be like part D of a problem. So, our given is going to be the moles of our limiting reactant. How many moles of limiting reactant did we have? Yep, 0.4455. And that was moles of NaOH, still same reaction. What we're going to solve for is the grams of H3P, it's just PO4, and that is used, or reacted, however you want to say it. Okay. So 0.4455 moles NaOH. The first step is going to be the mole-to-mole step. Moles of NaOH to moles of H3PO4. What numbers go in front of the moles? 3 on the bottom and 1 on the top, yep. Or 1 over 3. Where do we get those numbers from? The balanced equation, the coefficients. Mole to mole step is always going to be the coefficients. That's why we call it the coefficient ratio. And then we can go from moles of H3PO4 to grams of H3PO4. And we need the molar mass for this. It's 1 mole, and the molar mass, which we already calculated back in what would have been like part B, figuring out which one was our limiting reactant. What was the molar mass of H3PO4? No, 163.94 was Na3PO4. This one is 98. We did already calculate it, though in the heat of the moment, I can understand if you were in a test or quiz that you don't quite remember that you calculated. If you recalculate it and you do it correctly, you should get the same answer. Just provide, just do everything right and you'll get the right answer, right? Just do everything the correct way and you'll be fine. All right, so how many grams of H3PO4 were used during the course of this reaction? 14.55? And again, that is used. So to figure out how much actually remains, we're going to take the mass that we started with. What mass of H3PO4 did we begin with? 15.40. The amount given in the problem. So you go back to the beginning of the problem, you look at how much of that excess you started with. In this case, it was 15.40. Now that's how much we added like into the beaker where this reaction is occurring or whatever. And we used 14.55 grams. So we're going to subtract that, and that will tell us how much H3PO4 is left over. And that is 0.85 grams of H3PO4 remain. Not a lot. Not a lot. So like I said, this would be like the fourth part of a problem. There's one more. There's one more part. And that is percent yield. Percent yield. In our notes, we're actually going to do percent error and percent yield, but I'm mainly going to be, like percent error, that's old, that's an old hat. We've done that for a while now. Percent yield is the new stuff. But just to review percent error as well. Are we good? Okay. So first let's review percent error and then we'll talk about percent yield. So this is like what we were doing in our lab. So in the problem we were just doing, 24.35 grams of Na3PO4 should theoretically have been made. That's what we calculated from our stoichiometry. We said, oh, we should make 24.35 grams of sodium phosphate. But if I actually did this lab, what if I only got 21.50 grams? So 21.50 is my experimental value, and 24.35 is my theoretical value. So to calculate percent error, I'm going to take the absolute value of the theoretical, which is 24.35, minus the experimental, which is 21.50, all divided by the theoretical times 100. And remember, we do absolute value because we cannot have a negative percent error. So we just want like the positive difference between the two, what you got and what you should have got. And the lower the percent error, the better. Because percent error tells you kind of like how much error you had. So you don't want a big error. In your hydrates lab, you might have had like 1,000% error, depending upon how well you actually remove the water from the hydrate. What did you guys get for this? 11.70? And that is percent error. And the percent yield formula you have in your notes already. I'll flip over to that page in just a moment. This was also in your lab. So percent yield is just experimental over theoretical times 100. Okay? So for this experiment, our experimental is 21.50. Our theoretical was 24.35 times 100. While you guys are calculating that, percent yield is kind of tells you the efficiency of the reaction. The closer to 100, the better. Because you would like to actually get from your experiment or from your reaction as much as you should get. It is possible to get over 100% yield. It does not mean that that's better. It's not like extra credit on a test, like, yeah, I did over 100%. Getting over 100% yield, there is still an error. And it's likely caused by something, if you're doing like mass, it would be extra mass in your like beaker that shouldn't be there. Like most common cause of having greater than 100% yield, at least what you're going to see is something like, I don't know, there's water left in the beaker or on the underside of the watch glass that will be adding mass that really shouldn't be there. So keep that in mind as you're doing the rest of your lab calculations. What did this experimenter get as their percent yield? What'd you get? 88.30% yield. Okay. Now if you notice, for this case, our percent yield plus our percent error equals what? 100. That will always be the case if the percent yield is less than 100. If the percent yield is over 100, the percent error would be the amount that the percent yield is over 100. Okay? So yeah, that is like everything we're going to do for like limiting and excess reactants. We have one more problem that we're going to do. I'm just not going to record that one because that's just going to be practice. But you at least have seen how to do it, so you can always come back and watch this video again if you need a refresher on it. So I'm going to stop the video now, and we're going to do some more practice.